Hi, welcome to everyone. Today we are going to see about switch reluctance, hub motor design and numerical analysis using motor solver. This is for application to electric vehicles. I am Lenin, Associate Professor, School of Electrical Engineering from BIT University, Chennai. So first of all, why we go for electric vehicles? Three major aspects why globally people want to have electric vehicles when compared with conventional vehicles is to reduce the air pollution, to mitigate the global warming problems, and to reduce dependence on depleting oil resources. So these three are the major factors why the OEMs as well as the global government want to move from conventional vehicles to electric vehicles. Why we prefer switch reluctance machine compared with other electrical machines like induction machine, permanent magnet, synchronous machines, brushless DC machines and all. The advantage of synchronous machine, switch reluctance machine is there will be no permanent magnets, easy to fabricate, fault tolerant, better thermal capability, as there are no permanent magnets or windings present on the rotor, and it has the capability of high starting torque like DC series motor. If you see the construction of a switch reluctance machine, so both the stator as well as rotor is having salient ports, and stator is carrying windings, whereas rotor we don't have any winding or otherwise permanent magnets, and stator is having concentrated winding, so each and every diagrammatically opposite poles constitute a phase. So each phases are independently connected to each other, so it is highly fault tolerant. That means any fault occurs in one phase, it is possible to run the machine by having two healthier phases. And today we want to discuss about the design aspects of hub motor. That means your inner part is going to be a stator and your outer part is going to be a rotating ball. So in this design lecture, we choose 6 stator teeths and 10 rotor teeths. It's a 3-phase machine, whereas the stator teeths carrying the winding, whereas the rotor teeth doesn't have any permanent magnets or coils. So as far as dimensions are concerned, parameter and dimensions are concerned, so we are going to design a machine for a 48 volt system DC supply with a peak current of 35 amps. The rated speed is 500 rpm. The outer diameter of the rotor, that is here, the outer diameter is 180 mm. Air gap thickness, that is this one, the distance between the stator teeth and rotor teeth is 1 mm. Number of phases is 3, that is diagrammatically opposite phases constitute one phase. So 1, 2, 3, 3-phase machine. Total number of stator teeths 6, 1, 2, 3, 4, 5, 6, and total number of rotor poles is 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Rotor inner diameter, that is this is the rotor. Its inner diameter is this one, that is 128 mm. Rotor core thickness, that is the back iron thickness, is 14 mm. Rotor pole angle, that is the angle in the tip, this one is 22 degree. Stator ID, that is shaft diameter or otherwise stator ID, it is 38 mm. Stator OD, this one, this point is 126 mm, as the air gap thickness is 1 mm. So 1 mm, this constitutes 2 mm, so it is going to be 126 mm. Coil length, the coil length is 34.2 mm, this length, coil length. And the coil angle is 60 degree. slot depth is 36 mm, this one. The slot depth means this one, the depth. This is the slot, and the slot depth is 36 mm. Stator pole angle is 17 degrees. Number of turns as per the design, and number of turns is going to be 52. So as far as the current rating and number of turns is concerned, we use AWG 12 here, and during the design we assume that the coil fill factor is going to be approximately 50%, and the material for stator and rotor is going to be M19 silicon steel. So before going to get into this lecture, I would like to suggest go through this 4 lecture links before going to start the design of this one, so that it is easy to understand the design process of the entire machine, what we are going to discuss today. Okay, so this is the design lecture which uses motor solve to design this outer rotating or otherwise hub motor switcher reluctance machine. So now we are going to see the step-by-step process, how to design the machine and how to post-processing it and how to get the static results as well as transient results. So as already suggest, the specifications, whatever the specifications we get by means of analytical design, those things we are going to put it here. So if you see here, the first thing, go to the start and open the switcher reluctance machine page. Click the new button. In that we have 4 machines as far as the motor solve is concerned now: DC machine, induction machine, switcher reluctance machine, and permanent magnet machines. Choose the switcher reluctance machine, then you get a window like this, and click the prototype design. In that you open you just mark it supply voltage as 48 volt DC, rated current is 35 amps, that is peak 35 amps, rated speed is 500, outer diameter, this one is 180 mm, air gap thickness it's 1 mm, stack height is 32 mm, and rotor location is exterior. As I already suggest, this is the lecture we are going to see the outer rotating switcher reluctance machine. So the rotor location is exterior, and rotor type is, it's a general rotor type with 10 number of rotor teeth: 1 2 3 4 5 6 7 8 9 10. And stator type is also not a special type here, so it's a general stator type which is having 6 stator teeth: 1 2 3 4 5 6. So this constitutes a 3-phase machine. And if you want to add mechanical losses, you can add your mechanical losses like friction, windage, and stray load losses. The next thing is, click the general settings. Once if you click the general settings, the same is going to appear here, whichever you did it in the previous session in the prototype design one. Check twice all the parameters are going to be correct with the input whatever you given in the prototype design. So the next one is click the rotor. So the rotor here, it is going to be this one. This is rotor, and this is rotor back end, rotor teeth, rotor pole angle, and this is slot depth, and rotor inner diameter. So the inner diameter is going to be 128 mm, outer diameter is 180 mm. So inner diameter is this one, the tip. So core thickness is 14 mm. Core thickness means this back end thickness is 14 mm. Rotor pole angle is 22 mm. This is 22 mm. And tooth angle, this is a straight tooth angle, so I made this as a 90 degree. Suppose if you want any tapered or otherwise any angled, you can mark that angle either 60 degree, 40 degree, 45 degree as your wish. So similarly, if you want to have any pole bottom radius or otherwise pole tip radius, anything you want to have a special design, so you can do those things in this case. So having making this 0 instead of 0, if you make greater than 0, so automatically you can see the changes between bottom radius as well as tip radius. Once you finish this one, try to check twice whether you get the without any error the input values you are putting in the column is correct. Suppose if you make any mistake, this one is going to be highlighted in red. Whatever the input values you are going to survey, for example, instead of 90, if you put 180 here, suppose if the machine is not possible to do that 180 degree tooth angle, surely it is going to highlight in red color, so that you may change according to the correct design. So the next thing is we are going to design the stator, that is this part, the inner part. So if you see the inner part, which in this case it is going to be the static part. So the inner diameter is 38 mm. That is, as I already told you, the inner diameter is the shaft diameter. It is 38 mm. The outer diameter, that is this one, excluding the air gap. Excluding the air gap, it is 126 mm. So the coil angle is 60 degree. Coil bottom width is this one. The coil bottom width is 3.13. Coil length, this one. The coil length is 34.2 mm. Slot depth from this point to this point is 36 mm. And the stator pole angle is 17 mm. Tooth angle is 90 degree. That is, we didn't make any special pole, only we get the exact rectangle pole, so the tooth angle is going to be a 90 degree. And if you see here, you need to maintain this gap between two coils so as to reduce the mutual inductance effect. As well as we need to have insulation also, so that at least you need to maintain plus or minus 3 mm between these two things. So only I maintained coil bottom width as 3.13 mm, excluding the insulation at all. So bottom fillet radius is this one. So the bottom fillet radius is going to be 2 mm. So the gap between these two is going to be 2 mm. Suppose if you want to make this as 0 also, you can make this as 0. No, so this is according to my design. I make a bottom fillet radius as equal to 2 mm. So once if you finish the stator and you finish the rotor and stator with the coil, the next one is you need to give the number of turns and number of parallel paths in the stator winding. So the next one is how to give how many number of parallel paths. So as far as this design is concerned, it is going to be one parallel path, and already I suggest that we are choosing the AWG number as 12, and number of strands is equal to 1. So the number of turns per phase is going to be 52. Each coil, that is each coil having 52 turns. So coil 1 is going to be 52 turns, and coil phase 2 is going to be 52, and phase 3 is going to be 52 turns. So these are all the coil directions you may give, or otherwise manually this is going to be in the motor solve itself. So the advantage of motor solve is once if you fix the layout method as automatically this is going to happen in the software itself. So after that, the final stage is you need to incorporate stator end windings. In stator end windings, you can see this. This is the rotor core, and this is the stator coil, and the distance between these two is gap height is going to be 2 mm, and whatever the thing you want to make, that is height of the entire thing, and the height of the end coil. Fill factor is the fill factor what we assume is 50%, and now the fill factor is going to be, if you see in the winding detail itself, so it is clear the slot fill factor is 47.8%, and coil fill factor is 47.8 percentage, and conductor area is 3.3 mm square, bar slot area is 719.9 mm square. In left hand side you can see end winding resistance. The total resistance is 0.04567 ohms, and end winding inductance equals 71.63 microhenry. So the winding phase resistance, the entire phase, one phase resistance is going to be 0.0808 winding phase resistance. So end winding resistance means only this resistance, this end winding resistance, whereas this one is the phase resistance. So the entire phase resistance is 0.0808 ohms. So that's all about stator windings. And the next stage is it is going to be materials. As I already suggested, the material we are using for stator and rotor core. Stator and rotor core is M19 steel, and for windings it is copper, and air it is a common thing, it's a air, that's it. So inside this, because this is a non-magnetic material shaft, so we use the air, and here also it is air. So that's all about material settings and the MotorSolve software. Yes, this is the thing. So we are using a rotor back end material as M19 29 gauge thing, and stator material is also same thing, and rotor tooth material is also same thing. Stator tooth material is also M19 29 gauge. Stator coil material is copper, and slot liner material is epoxy resin. So after completing the design, you have to save the file. So go to save and save the file in any one of your drive, so that the first two things we can do in MotorSolve. One is static analysis, and another one is transient analysis. So the transient analysis, it took some time to get the results, but it is more accurate. It is real-time results, whereas static analysis we can get instantaneously. So it is easy to alter the dimensions up to your expectations, or otherwise up to your requirements, as easy as possible. So initially, whatever the design we are going to analyze in the finite element analysis platform, so the initial cases we need to finish the we need to study the static performance of the machine. So what we are going to do now is we are going to do the static analysis first, then we will go for transient analysis. So in the first transient analysis, what we are going to do is go to the result bar and click the result. So in that the performance chart, whatever the thing we can extract from the MotorSolve is listed here. So starting from flux linkage, inductance, static torque versus speed, and in analysis chart we have both static motion. So we can do this separately, as well as we can do these two things separately. And apart from this static and motion analysis, we have instantaneous fields. We have field line probe, field arc probe, and field point probe. That means we can probe the flux density, field intensity separately. So initially what I did is we will go for performance chart and check what is the flux linkage, inductance, static torque. So the first thing is flux linkage. I just click the flux linkage and plot the result. Click plot the result. So you may refer my previous lectures so that it is easy to understand how to do those steps and all. So once if you click and if you change this, here as far as that figure is concerned, I analyze for a peak phase current of 100%, that is 100% peak current with a current interval of 5. Number of rotor positions is 15. So current interval is 5, so only we get a 5 current intervals here. So this is for a 1, 2, 3, 4, 5 current intervals. So at 7 amps, 14 amps, 21, 28, 35. So if you want to have 10 intervals, you can change that as 10 intervals, or otherwise if you want only for 35 amps, you can give as 1, so that automatically it is going to come for a peak current. So if you see here, the flux linkage for 35 amps is this one. So this is at aligned position, this is at unaligned position. So if you see here at aligned position, it is around 0.121 Weber, and here in this case it is approximately 0.0423 like that. So this flux linkages is going to help. So if you want to optimize the machine, increasing the flux linkage is going to increase the inductance value. So increasing the inductance, it is going to increase the torque value. So likewise, you can change your design in each and every step. You can view the flux linkage plot. From the flux linkage plot itself, it is easy to understand how the torque of that particular machine is going to change. So the next one is the inductance plot. So inductance is flux linkage per unit current. So for each and every current, the same current, 7, 14, 21, 28, 35. So you can see the inductance plot for different currents. So this is for inductance flux linkage, and if you put flux linkage per unit current, you get the inductance value. So the inductance value for each and every current is plotted here. Say for example 7 amps, it is going to be around 10.2, 10.3 millihenries. See here it is millihenries. This is at aligned position. So this is at unaligned position. So the thing is, if you see at unaligned position, irrespective of the current, the nature of the switcher reluctance machine is it is going to be similar at the time of unaligned inductance, because the flux linkage is very, very small. So the inductance is also going to be same in this case. Whereas at the peak current of 35 amps, the inductance value is around 3.2, 3.4 millihenries. So using this data, you can easily compute what will be the torque in that particular machine. That is what we are going to see in the next step. So if you see here, again, see the current intervals here I increased to, instead of 5 it is 10. So we get up to 10 different plots. This is 3.5, 7 amps, the green color is going, this one is going to be 10.5 amps, like that, up to 35 amps. So if you see here, at the static position at 35 amps, the current is going to be approximately 13 Newton meter. So this is at peak current. So probably RMS current is going to be in between this one, 21 to 24.5. So at that time, the torque is going to be this one. Third, 4, 5, this one. So at the RMS current, so the torque of the machine is going to be between 6 and 10. So the probable torque we are going to get, we are going to analyze what is the torque and the transient if I apply the RMS also. Those things we are going to see. So as far as this basic performance chart is concerned, what we seen so far is, one is flux linkage, one is inductance, and one is torque. So based on this three itself, we can easily come to understand how far the machine performance is going to be for each and every current injection, how far the machine is going to deliver the torque irrespective of the speed. Because as this is a type of synchronous machine, whatever the switching frequency we are going to operate, based on that the rotor speed is going to be achieved. But as far as torque is concerned, it is directly proportional to the current. So whatever the current we are going to inject here, we can study what will be the torque, flux linkage and inductance of that machine, so that it is easy to understand whatever the speed of the machine, if we have that particular current, we can get that particular electromagnetic torque. So the next one we are going to see is in the static analysis itself, we may see different fields. So here, once if you click the instantaneous fields, in that contour plot you choose flux function, and in the shaded plot you choose flux density. So once if you choose the flux density, you can view the flux density at the tip of the teeth as well as other part of the machine also, so that you can rotate your machine in each and every position, each and every degree. In each and every degree you can view the flux density plot of the machine, so that you can understand whether the machine performs under the saturated region or otherwise nearby the saturated region, whatever the closest region it may be. But as far as the switched reluctance machine is concerned, if you operate at the saturated region, then the performance of the machine is going to be better. So again, if you drop down this shaded plot, keeping the flux function as it is, and change that instead of flux density, if you put radial flux density, so that you can get the radial flux density also, which is going to helpful for vibration studies. This radial flux density is going to helpful for vibration studies, which is going to be the radial flux density function is directly proportional to the vibration G level. So the next one is current density. This is going to be a vital in case of electromagnetic analysis. So the current density, if you see here, that up to the current density in the coil is 5.65 ampere per mm square. So current density, it is ampere per mm square, and the flux function is Weber per mm, and the current density is ampere per mm square. So the maximum current, the current density is approximately as 5.65 ampere per mm square. This is at current in and current out, so this is going to be minus 5.65 ampere per mm square. So another advantage with this MotorSolve software is it is easy to understand what is the relative permeability of each and every part of the machine. So if you see here, the relative permeability of steel, the stator and rotor is around 8,469 relative permeability, and if you see the coil and all, it is going to be the copper, and so each and every part. So the relative permeability of the machine, it is easy to plot, it is easy to get whatever the relative permeability the machine is going to use. So based on this relative permeability, you can easily you can verify the analytical solutions, whatever the analytical formula you used to design the machine. You can easily cross-check whether the same thing is going to happen in the software as well as in the analytical platform. So the next one is winding loss. What will be the total winding loss in the machine if you inject this much of current, that is 35 amps, that is percentage of rated current is 100 amps, 100 percentage, so it is 35 amps. For that 35 amps, so what will be the winding loss? So if you see the winding loss alone, it is going to be 3.09 into 10 power minus 7, that is a kilowatt per mm cube. So you need to calculate into watts per meter. Watts per meter meter cube. So the thing is, the next one we are going for instead of performance chart, we can go for static analysis. In static analysis, you can drop down this result quantities, and you can find out enormous things of result quantities like energy, co-energy, flux linkage, inductance, static torque. So many things are there. So each and everything you should have to drop down, and you have to analyze in the analyze each and everything, and you need to check with your analytical solutions whether the analytical solutions are going to correlate with the designed machine. So once if you do that, then if you go for transient analysis, you can get the real-time performance of the machine. So what I did is here, if you see here, I just make a energy and co-energy component, energy and co-energy component for different current intervals. The energy component and the co-energy component is going to be joule. the unit is joule for different rotor positions. So I get the co-energy value and energy value, so that you can get what will be the based on this you can plot the psi curve, and you can easily identify the workspace working point, or otherwise operating point of the switched reluctance machine. So far what we did is we will finish that static analysis, and in performance chart we will see flux linkage, inductance, static torque, and in static analysis we can have energy and co-energy. Based on that, it is possible to find the operating point of the switched reluctance machine. And in fields we have a different instantaneous fields from flux density, from permeability, current density, winding losses, everything. So up to this, whatever the changes you want to do, or otherwise whatever the optimization you want to do, you can carry over in this stage itself. No need to go for transient analysis. Once whatever the optimization you want to do, or otherwise whatever the structure you want to change here, say for example if you want to have a hole here, or otherwise if you want to have a arc here, or otherwise if you want to make a shape like this, or otherwise if you want to increase the rotor pole angle, or otherwise if you want to reduce the stator pole angle, whatever it may be. So you can do those things in the initial design stage itself, so that you can do the basic static analysis. And in static analysis you can go through these results and check, verify, and verify with your previous results. Once if the particular design is going to provide the better output, then based on that results you can go for doing the motion analysis, or otherwise a transient analysis. So that is what we are going to see now. What are all the things we can incorporate in the transient analysis. So in transient analysis we are having two things. Click the motion analysis in the result window, and in that if you drop down the display method, we have four different types of available in the display method. One is time average, one is waveform, another one is harmonic content in phases, harmonic content in harmonic content in phases. So the first thing is I make a display method as time average, and in result quantities I choose torque, output power, efficiency, and RMS current. So as the machine we designed is around we required around 525 watts. We designed for that 525 watts with a speed of 500 RPM. So the torque requirement is approximately 9 to 10 Newton meter. So the approximate efficiency we have shown is 85%. So we want to check whether those results are obtained instead of going for plotting the results for different speeds. Instead of that, straight away I can do the time average one and check what is the torque, output power, efficiency, and RMS current. Once if I display the X quantity is going to be default, that is with respect to the rotor position, and the rotor speed here it is rated speed is 500 RPM, and the peak phase current is 35 amps. So if I do that, and if you get the results, see whatever the result I get, I just so if you see this one, the output power, the torque what I want is 10 Newton, 10.1 10 Newton meter, it is satisfied, and output power it is going to be 0.526 kilowatt, that is I want 525 watts, so that is also achieved. Efficiency 85%, that is also nearby 85%, and RMS current based on the 35 amps it is calculated what is the RMS current for this particular speed the machine requires to produce the torque of 10 Newton meter. So once if I satisfy with the design requirements by having this time average chart, and you can add other things also. Once if you drop down this one result quantity, you are having losses in the winding, so many things are there, you can add those things and you can make a chart also. So once if we finalize your torque, output power, and efficiency is going to match with the speed, then you can go for analyzing the other charts by means of waveforms. So that is what I am going to do. So if you see here, I just in the display method, instead of choosing time average, I choose waveform, and in result quantities I choose torque, and x axis it is going to be the rotor angle, and I am going to analyze this torque value for one particular speed, that is at rated speed. So if you see, this is going to be the dynamic or otherwise transient torque graph for your designed machine. So the average of this one is going to be around 10.1 Newton meter. So that is what we saw here. 10.1 Newton meter is the average torque, and this is your instantaneous torque. See here, the peak current is going to be 35 amps, so that the RMS current is 24.2 amps, and your rated speed is 500 rpm. So at 500 rpm, if you inject a current of 35 amps in the stator winding, and if you apply the machine to run at 500 rpm, then at that particular time the machine is going to deliver this torque instantaneously, and the average torque is going to be 10.1 Newton meter. So the same thing, I just want to calculate the efficiency of the machine. So first I want to know the input power. What is the input power required at this particular speed, rated speed, at the rated current of 35 amps peak. So the input power is going to be around 1.6 kilowatt, 1.7 kilowatt with respect to the rotor position. Then the output power for the same condition, that is at the rated speed with the rated current, the output power exactly it is going to follow the torque developed by the machine, and the output power is this is the instantaneous output power, and the average output power is going to be somewhat here. It is going to be 526. This is the average output power, that is 526 kilowatt. Sorry, 0.526 kilowatt. So the next one is the current waveform for a one phase. So this is going to be started at here, and it reaches the peak of 35 amps, and it is going to drop down. So this is going to be 35 amps. During 35 amps, the machine is going to deliver 500 amps. So this is the loss in kilowatt, total loss in kilowatt. It is going to be around a 0.13 kilowatt. So this is the RMS voltage. See, at the RMS voltage for different speeds. So for different speeds, see at the rated speed 500 rpm, it is around 26. It is RMS voltage is around 26, and once if it reaches the steady state, once if it reaches, or otherwise there are two control techniques here we used. One is a voltage control method, and one is hysteresis control method. So up to this one we are using hysteresis control, that is up to 2000 rpm we use the hysteresis control. After this we are using PWM control. So up to this, current is going to be a variable one, voltage is going to be a variable one, and after this we are maintaining the voltage constant. So the RMS voltage is going to be around up to 48 volt. So we are using 48 volt DC here in this case, and this is the RMS current. So if you see this one, at the time of starting the current is more. Once the machine reaches at the maximum speed, that is 6000 rpm, the current is going to drop down to around 3 amps. So this is the RMS current required, around 22-23 amps, and here at 500 rpm this is going to be around 22 amps, and during 1000 rpm it is around 18 amps, and similarly at 3000 rpm it is going to be around 5.2, and 6000 rpm it is going to be around 3 amps. So this is for torque for different speeds. So for different speeds from 0 rpm to 6000 rpm, see the torque. So up to 500 it is going to be somewhat maintained constant, and after that it enters into constant power region. So the constant torque region is going to be up to 500, and after that it is going to be constant power region. So if you see this 1000 rpm, the torque delivered by the machine is around 7.5, and 2000 rpm it is going to be it is around 1.4 something, and during 6000 rpm it is 0.2, 0.3 newton meter. So the input power for different speeds is plotted here. So if you see here for 500 rpm, the input power is around this one. So this is some 0.6 kilowatt and all around, and it's 1000 rpm it is 0.82, and for 6000 rpm the input power is 0.18 kilowatt. So this is the graph shown input power as well as output power. The red color is input power and the green color is output power. So if you see this, each and every position, the input power is varying with respect, output power is varying in according to the input power. So based on this graph, the advantage in MotorSolve is, based on this you can easily calculate what is the efficiency of the machine at each and every speed, from 0 to maximum speed of 6000. If your vehicle operates at 6000 rpm, so you can easily calculate what will be the efficiency at each and every point. See the efficiency, based on this we calculate the efficiency, and see at 500 rpm it comes around 84-85 percentage, and in 1000 rpm it is going to reach us 90 percentage, and 6000 rpm it delivers 89% efficient. So the idea behind this design is we want to design 85% efficient machine at the rated speed. So this is the current density of that machine for each and every speed. So the current density at the start, that is going to be around 3.5 ampere per mm square at the starting. During the 500 amps it is going to be 3.4 ampere per mm square, whereas at the time of 6000 rpm it is going to be 0.5 ampere per mm square. So this current density value is going to be helpful in thermal modeling and thermal analysis of the machine. And the major advantage with this type of switch reluctance machine is, compared with induction and other type of machine, is torque per unit volume of the machine is very high. So if we want to compare the torque per volume between the machines, so this thing, it is happened in a transient analysis. You can perform a transient analysis and you can get the torque per unit rotor volume, kilonewton meter per meter cube. So if you see this, the torque per newton volume at the steady state, that is constant torque region, it is around 18 kilonewton meter per meter cube, whereas at the maximum speed of 6000 rpm it is going to be 0.2. So reducing the rotor volume and keeping the torque maximum is one of the biggest challenge in electric vehicle application. So that is what people are doing as the optimization techniques. Those techniques are useful in this particular MotorSolve platform. And another thing, as far as vibration and noise issue is a vital thing in switch reluctance machine. So this air gap stress is going to be directly proportional to the vibration and noise of the machine. So predicting this air gap stress is also another challenge in switch reluctance machine, as this MotorSolve platform is directly provided the air gap stress in Newton per mm square in each and every speed of the machine. It is easy to predict what is the G level and noise level, dB level of the machine also. So as far as air gap stress is concerned, if you see the plot is for different speeds, the air gap stress is going to be 0.009, nearly 0.00, 91 for a rated speed, and it keeps on decreasing for over the period of rotor speed. So this is because each and every rotor speed, the current value is going to be decreased, so the stress is also going to decrease. And if you see the losses, total losses, this is going to be the total loss of the machine for each operating at each and every speed. So say for example at 500 rpm it is 0.075 kilowatt, and in 3000 rpm it is around 0.031 kilowatt, and in 6000 it is going to be 0.0. So the copper loss plays a vital role here, and once this 2000 rpm exits, windage loss is also going to be a vital case. So this is the plot which shows the losses only in the winding, that is copper loss. So for different speeds. So these are all the advantages of this motor solve platform. So we can measure the losses in each and every part of the machine separately, so that whatever the optimization process you are going to incorporate in your design, each and every stage you can compare all the models with all the losses, so that it is easy to come to one conclusion in which model, in which aspect the losses is going to reduce or increase in which part of the machine. So this one, it is going to show the loss in the winding for each and every rotor speed. So if you see this one, the case is 500 rpm, it is around 0.066263, and in 2000 rpm it is going to 0.008, and in 3000 rpm it is going to be keep on decreasing. As the current is going to decrease, I square R loss is also going to decrease. So this is stator back end hysteresis loss for each and every speed. Similarly at 500 rpm it is 0.00025, 1000 rpm it is 0.004, and 2000 rpm it is 0.0032, and 4000 rpm it is 0.00225, 0.00225, and 5000 rpm it is 0.002. So similarly at 6000 rpm it is around 0.0017178. So the next one is stator back iron eddy current loss. So we can the software splits the iron loss into two, hysteresis loss as well as eddy current loss, so that it is helpful to whatever the steel you are going to use, whatever the flux density you are going to obtain by means of that steel, and whatever the frequency you are having in that particular steel, you can easily incorporate what will be the eddy current loss as well as hysteresis loss in that machine. So if you see here, so during at 500 the frequency is very less, so the eddy current loss is very less. So once the frequency increases, the eddy current losses keep on increases, and in after 1500 the eddy current loss is somewhat constant throughout the maximum speed of the machine. It's around 0.00121, whereas at 500 rpm it is going to be around 0.005. So everything it is in kilowatt, so just convert into watts to calculate the efficiency of the machine or total loss of the machine. So the next one is loss stator teeth. Stator teeth, this is also another one plus. Suppose if you want to optimize the stator teeth with different shapes, each and every shape it is going to give different stator teeth hysteresis eddy current, so that it is easy to optimize the machine also. So if you see the stator teeth hysteresis, you can see that 500 rpm it is around 0.004 kilowatts, 1000 it is going to be 0.0082, and 4000 it is 0.0055, and 5000 it is around less than 0.005, and 6000 it is less than 0.00, it is approximately 0.0044. And here stator teeth eddy current is also available, and similarly at 500 rpm it is around 0.00055 kilowatt, and 3000 rpm it is 0.00225, and 5000 watts, so somewhat near to that 0.0025. So similarly, we can have a rotor back iron hysteresis loss, rotor back iron eddy current loss, rotor teeth hysteresis loss, rotor teeth eddy current loss. So this is the final chart you can have in the motor solve in the transient analysis. You can overlap all the chart that is with respect to the efficiency, torque, efficiency, torque, output power, current with respect to the rotor speed. So if you see here, the blue graph shows the efficiency for different rotor speed. So at 500 rpm, I just highlight the value of 500 rpm. See, the rated speed is 500, output power is nearly 500 watts, torque is nearly 10 Newton meter, RMS current is 21, efficiency is going to be approximately 85%. So similarly, if you have the same thing for a different speed, you can get what is the efficiency, and so there will be slight discrepancy between static analysis and motion analysis previously you done, because if you want to run this machine for different speeds, we need to specify the on time and off time. Based on that on time and off time only, this results we are going to off time. So calculating that on time off time is going to change your output performance of the machine. So based on the on time and off time only, we get this values. So there will be small discrepancy between efficiency, current, torque, output power, even in the losses also. So this is the chart. This is the chart one. It is going to explain the entire story of the design machine. So the advantage is you can have this chart including with the voltage graph, stresses plot, everything all together. Only for more clarity purpose, I include four different outputs with respect to the speed, that is torque, output power, efficiency, and RMS current. This side 2 and this side 2. That's it. So the blue graph corresponds to the efficiency, a red graph corresponds to torque, and this gray graph corresponds to current, and green graph corresponds to output power. And that's all about motion analysis with waveform. And the another option in the motor solve is one can easily understand what will be the harmonic orders in the voltage as well as current, everything. So here, if you see here, result quantities, display method, you drop down the display method, then choose harmonic content amplitude, then you will choose voltage. In the result quantities, I choose voltage here, and phase to display is A phase. Whatever the if you want to display all the three phases at a time, you can choose all the three phases, or otherwise what phase you want to display, you can display. See, other things, the rotor speed, everything, it is going to keep common as that of your transient analysis. So if you see the plot harmonic content amplitude of the voltage, so this is the voltage at different speeds, 100 rpm to 6000 rpm. So these are the voltage plots. So if you see this one, one can get the harmonic order as well as what is the amplitude of that harmonic voltage level for each and every speed. This is going to helpful to find the total harmonic distortion as well as ripple content, everything. So the next one is what will be the torque harmonics present in the torque. So this is going to helpful in calculating the torque ripple, which is going to proportional to your vibration and noise. So this is also, we plotted it for different speeds from 100 to 6000 rpm. So this is the harmonic order for input power for different speeds. This is the harmonic order and this is the input. Y-axis is the input power, and this is with respect to different speeds. So similarly, for an output power for different speeds, the harmonic order or the content of the harmonic order are displayed here. So the final thing is the current harmonics we can plot it for different speeds for a phase A. So if you want to overlap all the three phases, you can overlap and you can show it. You can see it. So the next one is the previously what we see here is harmonic content amplitudes, whereas the next one we are going to see here is harmonic content phases. We are going to see is harmonic content phases. So in this you can choose the voltage. The similar things are available: voltage, current, torque, everything is available, and phases also it is available for different phases. So the first thing is I have put a voltage. So this is the harmonic content for different speed, that is 100 to 6000 rpm, and this is the phase angle for voltage. So different phase angles you can get. So similarly for current, different for phase angle, your harmonic content is this one for with respect to different speeds. If you see here, the harmonic contents are also there with respect to the phase angle. And finally, one can have a entire look or otherwise overall look of the design machine based on the performance indices. So this is the plot which is available in the motor solve. One can have a design index. In that design index, you can plot the entire performance parameters like torque, input power, output power, efficiency, RMS current density, torque per unit volume, air gap stress, loss, design index, everything all together with respect to any one of the design parameters. So here I plotted for output power. So for different output power, say for 1000 watts to 200 watts, 300 watts, 400 watts, 500 watts, 600 watts and 700 watts. So what will be the change in each and everything? Stress, current density, current density, efficiency, torque, output power, RMS current, torque per unit volume and total losses. So this is the plot one which is going to give the entire idea about the machine which we designed so far. The entire performance chart of the machine all together, so starting from the static to the transient, all together it is possible to plot to plot in a single window, so that it is easy to understand the entire design design information about the machine. So as far as this design is concerned, we are only intended to design the outer rotating hub motor for an output power of 500 watts for a rated speed of 500 rpm. So the approximate efficiency we plan to achieve is 85%, which we satisfy by means of this software design. So thanks for watching. So any queries you can post it through my video. Thanks for watching.